Today we shall consider proof by induction. We want to prove some property P x for all of x P of x for an underlying set. If an underlying set can be inductively defined, then we can use proof by induction. Let us call what is meant by inductive definition of set. Inductive definition of set has three parts. One part is the basis or the basis class, which tells you what are the basic building blocks of the set. The second part is the induction or the inductive class, which tells you how to build more and more elements of the set from already existing elements of the set. It establishes the ways in which elements of the set can be combined to obtain new elements. Okay. Apart from that, there is another class which is called the extremal class, which is the same for any definition, that tells you that no object is a member of the set S unless its being so follows from a finite number of applications of the basis and the inductive classes. Or it can be said in somewhat different ways also, the set is the smallest set which satisfies the basis and the inductive classes. This extremal class is the same for all definition of inductive definition of sets, but it has to be mentioned explicitly. Now let us consider proof by induction. Let us take some underlying inductively defined sets. For example, in the last class we considered well formed strings of parenthesis. How did we define this? Basis class, this belongs to if you call the set B, and the induction class is if x comma y belong to B, then x belongs to B and also x y belongs to B, and then you have to mention the extremal class. Now we want to prove some property of this class. Let x be a well formed string of parenthesis L of x denotes the number of left parenthesis, R of x denotes the number of right parenthesis. Now we want to show that if x is a well formed string of parenthesis, then L of x is equal to R of x. Number of left parenthesis is equal to the number of right parenthesis. This you know already, but let us see how to prove it by induction. The proof by induction has two parts, the basis part and the induction part. The basis part is like this. You prove this property for the elements which belong to the basis class. So here this is the element which belongs to the basis class, and more elements are built by using this in the induction class. So in the basis class of the proof, you prove the property for this, and in the induction class of the proof you prove the property for this, assuming that the property holds for x and y. So let us proceed now. So in the basis class, this is the basic building block of the set, and for this you know that L of x is equal to 1 and R of x is equal to 1. Therefore L of x is equal to R of x. Now in the induction class, you assume that the result holds for x and y. Let x and y belong to B. Therefore, the property holds for them. Therefore, L of x is equal to R of x and L of y is equal to R of y. Now, how more and more elements are built from this? Now, you know that the definition says that this belongs to B. Now, what is the number of left parentheses of this? The number of left parentheses of this is the number of left parentheses in x plus 1. And what is the number of right parentheses here? Number of right parentheses in this is number of right parentheses of x plus 1, and you can see that these two are equal. So, you are proving the property for the induction class. Now, the other part is, you also know that x y also belongs to B. If x belongs to B and y belongs to B, x y also belongs to B. This is the way we define the induction class. Now, for x and y this holds. Number of left parentheses of x is equal to number of right parentheses of x, and similarly for y. Now, what can you say about the number of left parentheses of x y? This is equal to number of left parentheses of x plus number of left parentheses of y. And what can you say about the right parenthesis of x y? That is equal to right parenthesis of x plus right parenthesis of y. And you know that this is equal to this and this is equal to this. So, these two are equal. So, we are proving the property for this also. And how are the elements built from the basic building blocks? So, if you in the induction class you say that if x y belongs to B, this belongs to B and x y also belongs to B, and for both these you are able to prove using induction. So, this is the way the proof by induction goes. The main part is the underlying set has to be inductively defined. Now, we know that the set of non-negative integers are natural numbers is inductively we can define. We can take this as the underlying set, and if you want to prove some property for this, you can prove P0, and then you can prove that if it holds for n, it holds for n plus 1, there is some property. If it holds for n, it holds for n plus 1, and from this you can conclude for all of x, P of x. Okay. This is what you prove. What you have to prove is P0, and then for all of n, P of n implies P of n plus 1. Then from this you can conclude for all of x, P of x. Okay. So, let us take one or two proofs in this manner and see. Sigma I is equal to, again you can take 1 to n, but you can take 0 also. If you take 1, it will hold for, it will start from 1. Let us take for 1, I is equal to 1 to n is I n into n plus 1 by 2. Take the basis 1, what can you say? Even if you take 0 it will hold, but let us take 1. What is P of 1? Just 1 sigma 1, that is sigma 1 is equal to 1 only, and here if you substitute a value of 1 for n, what will you get? 1 into 1 plus 1 by 2, that is 1. So, the left hand side is equal to the right hand side, and so for the basis you have proved. Now, the induction part you have to show that assume the result is true for n, then you have to prove for n plus 1. So, what you know that sigma I is equal to 1 to n, I is equal to 1 to n is equal to n into n plus 1 by 2. Now, what you have to prove is sigma I is equal to 1 to n plus 1, I is equal to, instead of n you must get n plus 1. So, you must get n plus 1 into n plus 2 by 2. So, let us see how to prove it. Sigma I is equal to 1 to n plus 1 is equal to sigma I is equal to 1 to n plus n plus 1. And by induction hypothesis we know that this is n into n plus 1 by 2. So, this becomes equal to this, and taking n plus 1 out you get this is n by 2 plus 1, that is equal to n plus 1 into n plus 2 by 2. Okay. So, this is the way proof by induction is used, and the thing is there is no extremal class or something like that in the proof by induction. In the inductive definition of the set you have basis class, induction class and extremal class, and in the proof by induction you have only the basis part and the induction part, induction hypothesis. Let us take one more example. Let A be a real number then A power 0 is 1. You know that A power 0 is 1. You define A power n plus 1 as A power n into A. This is the way it is defined. The number is defined this way. Now, you want to prove A power n into A power m is equal to A power n plus m. You want to prove this. How do you prove? First, basis class. Here m is a natural number. So, for basis class you take A power 0, A power n into A power 0, that is you are considering the case where m is equal to 0. This will be A power n into 1, A power 0 is 1, and that is nothing but A power n plus 0. Same as A power n, right. Now, the induction class is A power m, A power n into A power m is equal to A power n plus 1, n plus m. Assume this, and you have to show that A power, to prove, you have to prove A power n into A power m plus 1 equal to A power n plus m plus 1. So, you have to prove A power n into A power m plus 1. How will you write this? A power n into A power m into A, and by induction we know that this is A power n plus m. Now, A power n into n plus m into A will be A power n plus m plus 1. This is by definition, and because of associativity property for non-negative integer, this you can write as A power n into m plus 1. So, this result is proved. Okay. Just to show the use of induction, I shall use one or two more examples. Let us consider some more examples, so that this concept of proof by induction is clear. prove that the number of diagonals in a n-sided convex polygon is n into n minus 3 by 2. Now, when you talk about a convex polygon, you can only talk about side 3 first. Side 3 it is a triangle, side 4 it is a quadrilateral, side 5 it is a pentagon. So, as a basis class, what is the number of diagonals in a triangle? You can even use 3, 4 and 5 for the basis class. It is enough if you prove for 3 or 4, but let us consider even for 5 to verify. What is the number of diagonals in a triangle? N is equal to 3, diagonals is 0. In this result, substitute 3, you will get 0, isn't it? N into n minus 3 by 2, if you use 3, you will get 0. When you consider a quadrilateral, the number of sides is 4 and the number of diagonals is 2. You will have 2 diagonals like this. So, use 4 in this equation, you will get 4 into 4 minus 3 by 2, which is 2. So, it verifies this result. Now, consider n is equal to 5, it is a pentagon. In pentagon, how many diagonals you have? Let us see, 1, 2, 3, 4, 5, 5 diagonals you have. So, the number of diagonals is 5 and use 5 in as n in this equation, you get 5 into 5 minus 3 by 2, that is equal to 5. Okay. Now, the induction class is proved like this, inductive portion. Assume that the result is true for n, assume that the result is true for n. That is, for a n-sided polygon, number of diagonals is n into n minus 3 by 2. What you have to prove is, for a n plus 1 sided polygon, the number of diagonals will be n plus 1. Instead of n, you must write n plus 1. So, this will be n plus 1 into n minus 2 by 2. Let us see whether we get it. So, consider a n-sided polygon. From this, I want to consider a n plus 1 sided polygon. I have to add one more vertex and this side and this side. If I do this, I get a n plus 1 sided polygon. So, how many diagonals I will get? The number of sides has become n plus 1 now by adding one more vertex. So, what is the new number of diagonals? Number of diagonals in this n plus 1 sided polygon. See, n plus 1 sided means n plus 1 vertices. It will have the same number of vertices. Already what are the diagonals here? They will also be existing here. So, those n into n minus 3 by 2 diagonals will be there, plus each of this vertex you can join with any one of the n minus 2 vertices to get one more diagonal. So, you will get n minus 2 diagonals like that plus one more diagonal. This side becomes a diagonal here. Now, if you sum it up, it will be n squared minus 3n plus 2n minus 4 plus 2 by 2, which is equal to n minus n squared minus n minus 2 by 2, and that is nothing but if you factorize, this is n plus 1 into n minus 2 by 2. So, the way you got the new diagonals is you are for the n-sided polygon you added one more vertex and two sides. So, already the diagonals you had here are present here also, plus this one has become a diagonal now, and this vertex can be joined with any one of the n minus 2 vertices to get one more diagonal. So, it is n minus 2 plus 1, and if you simplify this expression you get n plus 1 into n minus 1 by 2, and so we have proved the result. This is the way you proof by induction. So, starting with P0, if the underlying set is the set of non-negative integers, you prove P0 as the basis and then you assume Pn and you prove Pn plus 1. So, for all of n, Pn implies Pn plus 1, and from this you can conclude therefore, for all of x P of x. Now, sometimes as in the case of the diagonal, it does not make any sense to talk about diagonals of a one-sided polygon or a two-sided polygon. The smallest polygon is three-sided, which is a triangle. So, instead of starting with P0, you start with P3 here, k is 3. So, in some cases you may not start with 0, but you may start with some particular k. So, you prove Pk and you assume that the result is true for n and prove that it is true for n plus 1. So, you prove that Pn implies Pn plus 1, and so from this you can conclude that if x is greater than or equal to k, then Px will hold. Okay. This is the way you prove. This is called the first principle of mathematical first principle. First principle. And sometimes this is also called as weak induction. Weak induction. In contrast to that, what is called strong induction or second principle? What is called second principle or strong induction is this. For proving Pn, earlier we assumed only Pn minus 1. Okay. So, or for proving Pn plus 1 you assumed only Pn, or to prove Pn you assumed only Pn minus 1. Here for proving Pn you assume P0, P1, P2, P3 up to Pn minus 1. For all k less than n you assume Pk, then all of them are used to prove that Pn is true. The induction hypothesis is stated in this manner. So, what you do is for all k, if k is less than n, then Pk is true. That is P1, P2, P3 up to Pn minus 1 is true. Making use of all the facts, you prove that Pn is true, and from this you can conclude for all of x P of x. Now, in this case you need not have to write a P0 separately. The reason is when n is equal to 0, k less than n is false. So, this implication is true, and so automatically P0 will become true. P0 will automatically become true by this statement. The reason is k less than n, when you put 0 is false. So, the implication will be true, and so P0 will become true. Okay. So, where do we make use of second principle or strong induction? Again, let us take one more example. prove that the sum of the interior angles of a n-sided convex polygon is 2n minus 4 right angles, 2n minus 4 into pi by 2, or you can write it as n minus 2 into pi if you want. Now, how do we prove that? Basis class, as I told you again, basis class you start with n is equal to 3, you take a triangle. What is the sum of the interior angles of a triangle? It is pi, 180 degrees or pi. So, in this expression you put n is equal to 3, you get pi. Okay. Now, the induction class assume that the result is true for n is equal to 3, 4 up to say k minus, for I will put k is equal to n minus 1, prove for k is equal to n. Okay. How do you prove this? Take a n-sided polygon, n-sided polygon. Take two vertices and join them by a diagonal. So, it becomes two polygons put together, and the sum of the interior angles of the whole polygon is the sum of the interior angles of polygon 1 and polygon 2. The sum of the interior angles of polygon P is equal to sum of the interior angles of polygon 1 and polygon 2. How many sides that does one polygon 1 have, and how many sides does polygon 2 have? Now, the n sides is divided into say k into n minus k by this diagonal. So, the sum of the interior angles of polygon P is equal to, what is the sum of the interior angles of this polygon? This has got k plus 1 sides. So, that is k plus 1 minus 2 into pi. And what is the sum of the sides for this? That is n minus k plus 1. So, the sum of the interior angles is this minus 2 into pi. So, that will be equal to k minus 1 plus n minus k minus 1. So, this k and k will get cancelled, and you will get n minus 2 pi, which is the result we want. So, in this case you are not using the result for n minus 1 and proving for n, but you are using the result for k and n minus k and using it to prove the result for n. So, this sort of induction, where in order to prove a result P n, you make use of results P1, P2, P3 up to Pn minus 1, that is called second principle of induction or strong induction. Now, as far as the set of natural numbers is considered, n is equal to 0, 1, 2, etc., both have the same effect. In one case you prove P0, and using P0 you prove P1, and using P1 you prove P2, and using P2 you prove P3, and so on. This is weak induction or first principle. In the second principle or strong induction, you use first you start with P0, then use this to prove P1, and to prove P2 you use both this or sum of this. Then to prove P3 you make use of all this or sum of this, and then to prove P4 you make use of all these or sum of this. Anyway, the effect is the same, but there are other underlying sets for which you may not be able to use the first principle, but you will be able to use the second principle only. One such thing is the set of ordered pairs n cross n. If you take, say, the set of underlying set as the set of ordered pairs n cross n, so it consists of integers ij, and if you look at the plane, they can be looked at as grid points, okay, and you can introduce some sort of an order such that all these two numbers ij and kl, you can say this will come before this if I is less than k, or if I is equal to k, j will be less than l. Like that you can define, that is all these points will come before all these points. If you do like that, you will realize that in order to prove some result for this, you have to assume that the result holds for everything, because if you assume something is true for this alone, it will be true for this, it will be true for this, it will be true for this, and so on, but you will never be able to prove this result for this point. The reason is every point has a unique successor, but some points do not have a unique predecessor, because it goes up to infinity. For such underlying sets, you will not be able to use the first principle of mathematical induction, you have to use the second principle of mathematical induction. We shall learn about this again when we consider partially ordered sets, linear sets, well ordered sets, and so on. Let us take one example and see how you can use Venn diagram to solve some problems in set. So, just a simple example. A survey was conducted among 1000 people. Of these, 595 are Democrats, 595 wear glasses, and 550 like ice cream. 395 of them are Democrats who wear glasses, and 350 of them are Democrats who like ice cream, and 400 of them wear glasses and like ice cream. 250 of them are Democrats, they wear glasses and also they like ice cream. The question is, how many of them are not Democrats and they do not wear glasses and they do not like ice cream? The second question is, how many of them are Democrats who do not wear glasses and who do not like ice cream? Okay. So, using Venn diagram, let us see how the figure looks like. The totally there are 1000 people, total number of people, because the survey was conducted among them, of which 595 are Democrats. So, this is 595, and 590 of them wear glasses, and what is that? 390 of them are both Democrats who wear glasses, 550 are who like ice cream, and so on. So, let us fill these portions. How many of them are Democrats and who wear glasses and who like ice cream? 250. So, the intersection of all the 3 is 250. They are Democrats who like ice cream and who wear glasses. 395 of them are Democrats who wear glasses. Which this portion tells you Democrats who wear glasses. There are 395 of them, of which those who like ice cream form 250. So, the remaining is 145. So, put together it becomes 395. So, that portion is 145. And how many of them are Democrats and who like ice cream? 350 of them are Democrats who like ice cream. So, this portion is 350, out of which 250 is here. So, this portion is 100, right. And how many of them are wear glasses and who like ice cream? 400 of them wear glasses and who like ice cream. So, this will be 150. So, totally how many Democrats are there? There are 595 Democrats. So, this whole portion is 595, out of which you are accounting for 100 plus 250, that is 350, 395, 495 you are accommodating here. Total is 595. So, this portion will constitute 100. And similarly, 590 of them wear glasses, and how many of them you are accommodating here? 150 plus 250, 400, 445 you are 545 you are accommodating here. So, 50 of them will be in this portion. And similarly, 550 of them like ice cream, out of which 400 plus 100 you are accommodating here. So, this will be 50. The question is, how many of them are not Democrats who do not wear glasses, who do not like ice cream? That refers to this portion. This portion. How much is this? From 1000 you have to subtract the sum of all this. What does this sum lead to? This leads to 100, 145, 250, 100. This will add to 595 actually, because we know that the number of Democrats is 595. So, 595 plus 50 plus 150 plus 50, which will add to 19, 24. Right, 250, 350. So, the number of people who are not Democrats, who do not wear glasses and who do not wear ice cream will be 1000 minus 845, which is 155. This is the answer. And the second part is, what is the number of Democrats who do not wear glasses or who do not like ice cream? That from the figure we can see that this portion denotes the number of Democrats who do not wear glasses or who do not like ice creams, and you can see that this is 100. So, for the second part the answer is 100. Like that you can use a Venn diagram to solve some problems in set theory. This you would have done in school itself. It is just to refresh your memory. Now, let us consider some more thing about natural numbers. We tried to define the natural numbers inductively. How did we do that? We started with the basis class 0 belongs to n. What are the natural numbers or non-negative integers? They are 0, 1, 2, 3 and so on. So, we try to define like this: 0 belongs to n, and the induction class we said if n belongs to n, then n plus 1 belongs to n. but there is a small difficulty here. And what is the difficulty? We try to use addition for defining natural numbers. Usually after defining natural numbers only we define addition, that is the procedure. It is a chicken and egg problem. You cannot define natural numbers using addition, because addition itself you have to define using natural numbers. So, instead of saying like this, you say if n belongs to n, n dash belongs to n, where n dash is the successor of n. N dash is the successor of n. I can write fully successor of n. So, the natural numbers you can define like this. Basis 0 belongs to n, and induction class is if n belongs to n, then n dash belongs to n, and the extremal class is if n is contained in n and satisfies classes 1 and 2, then S belongs to n. Actually, you want something like this. You want to start with 0, then the successor of 0 is 1, then the successor of 1 is 2, then the successor of 2 is 3, and so on. But by this definition, do you get this? Do you get this diagram by what we defined earlier? By this definition, will you get this? There are some difficulties. For example, suppose you say 0 is the successor of 0, then you will not get a figure like this, but you will get a figure like this. 0 is the successor of 0, then again the successor, again the successor, and so on. This is what? Is this what you want? You do not want this. So, what do you want? You want something like this. Okay? So, this should not be permitted. So, you cannot have 0 as the successor of any number. And even if you allow that 0 is not the successor of any number, you may get a figure like this. For 0, you may have 2 successors, 0 dash and 0 1 dash and 0 2 dash, and for this itself you may have 2 successors, and for this again you may have 2 successors, and you may get a figure like a tree. What you want is a line, that is what you want, but by definition it is possible to get such a thing also. And what is that which gives rise to such a tree? Because you are having 2 successors for 0 and 2 successors for this, 2 successors for this, and so on. In order to avoid such a tree diagram, what you must say is the successor of a number is unique. You cannot have 2 different successors, but the successor of any natural number is unique. Now, suppose you say that 0 is not the successor of any number and the successor of a number is unique, then can you get this diagram? Then also there is some difficulty. You avoided this, but what about this? Suppose this is the successor of 0 and this is the successor of 1 and this is the successor of 2, 3 is the successor of 2. Suppose I say 2 is the successor of 3, then again 3 will be the successor. Successor is unique, successor of 2 is unique, 3 is unique, again the successor of this is unique, and so on. But you do not want what you want to get, but you get something different. And what is the problem here? See, the problem here is the predecessor is not unique. What is the predecessor for this? The predecessor for this is this as well as this. Okay? because the successor, you are marking the arrow like this. So, the predecessor of this is this, and because of this the predecessor is this. You are getting 2 predecessors for this number, which is not correct. So, the next condition you have to include is that the predecessor of a number is unique. So, we come to this definition. Actually, the set of natural numbers is defined using sets like this. Phi denotes 0, then phi union phi denotes 1, then phi union phi union phi comma phi, this denotes 2, and so on. Like that you can represent the natural numbers using sets. If you make use of this definition, we can define like this. Phi is a natural number. For each natural number n, its successor n dash is constructed as follows. If n is a natural number, then n union n dash, n union n denotes n dash, which is the successor of n. Okay. So, if you define like that, what will be 3? So, the phi union phi is, it is just having one element, right. Then phi union this is having only 2 elements like this. This is union phi is empty. So, the number 3 will have elements phi, 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 this has got 3 elements, that is this n union, this put within parenthesis. So, this will have 3 elements. So, n, if you take n union and n put within parenthesis will give you the next number n dash. So, if you want to write everything, 0 is empty, 1 is having only one element like this, 2 is having phi, comma phi, 3 is having phi, comma phi, comma phi, comma phi, and 4 will have and so on. So, you see that if this is n, n dash, the successor of n, contains all this plus this within flower brackets. This is n and this is n within flower brackets, that denotes the next integer or the success. So, we can define natural numbers this way and mention the constraints also. A definition of n which satisfies all of these constraints can be constructed using set theory. This is what we have seen. Phi is a natural number. Then if n is any natural number, then n union n is a natural number. The extremal class is the same as before. So, the definition is like this. The set of natural numbers n is the set such that phi belongs to n. If n belongs to n, then n union n within flower brackets belongs to n. The extremal class is if S belongs to n and S satisfies classes 1 and 2, then S is equal to n. The 3 conditions we can state as theorem. 0 is not the successor of any natural number, and the successor of any natural number is unique, The third theorem is the predecessor is unique, that we can state like this: if n dash is equal to m dash, then n is equal to m. That is, if the successor of n and m are the same, then n is equal to m. These are called Peano postulates for natural numbers, and we can mention them like this: Peano postulates. A, 0 is a natural number, then for each natural number n, there exists exactly one natural number n dash, which we call as the successor of n. In the second class itself, we are bringing out the fact that the successor is unique. Third is 0 is not the successor of any number, and the fourth one is the predecessor is unique. That is, if n dash is equal to m dash, then n is equal to m. The last one is the extremal class, which is like this: if S is a subset of n such that 0 belongs to S and n belongs to S, then n dash belongs to S, then S is equal to n. This is the usual extremal class. So, we can define natural numbers in this way using Peano postulates. So, we have seen what is meant by the inductive definition of sets and how we can use the inductive definition for proof by induction. In both cases, weak induction are the first principle and strong induction the second case. Okay. Then now we have also seen how the natural numbers can be inductively defined using Peano postulates.